So today we're making a shift. We're moving away from working purely with right triangles in regards to trig. Now, before we can truly make that leap and do trig with non-right triangles, first thing we have to do is we got to learn a little bit more about angles. Now, y'all have dealt with angles before. Geometry. You learn some things like, if I have two angles hanging out right next to one another, I can add them together to make the bigger angle. You learned angle addition postulate, in other words. But otherwise, when it came to angles and what you did in geometry, most of the time, you found angles inside of a shape. The corner of a triangle, the angle within a pentagon, angles within parallelograms. Generally, they were all kind of hanging out in something, or they were creating a specific format like vertical angles or linear pairs. But when it comes to angles, they are a lot more complex than just fitting in shapes. And on top of that, they're a lot more complex in what their measurements can be. Now, angles in their most basic format are generally sitting on top of a coordinate grid. Especially if we want them designed to be in what's known as standard position. So let's say I have an XY axis. Here's my coordinate grid. I want to talk about an angle in standard position. It has some specific features to it. First off, an angle in standard position have its vertex at the origin. What's the origin? Coordinate point 0, 0. Okay, what's a vertex? The corner, it's the pointy part of the angle. An angle is made up of two rays that intersect at a point, and that point is the vertex. So the vertex is at the origin, the pointy part of the angle is right here. What's known as its initial side will be on the positive x-axis. What is the positive x-axis? The horizontal axis to the right. What's known as the terminal side will be anywhere else. It's not a requirement of standard position, so I don't write it over here, but the second side of the angle is called the terminal side, and I'm going to draw the terminal side over here. Now, if you hear that sides of an angle are referred to as initial and terminal, what are other words for like initial and terminal? First and last. Start and end. Angles now have a starting position and an ending position, indicating that they have direction involved in them. In the past, when you dealt with angles, you didn't give them a direction. You just talked about their measurement being whatever the number of degrees between one side and the other side is. But that is not 100% true. Angles do have direction. And when we draw them out, we will have an arrow that indicates that direction. But more specifically, it not only indicates the direction, it also indicates the path that the angle followed. Now that piece is important, that indicating the path that it followed, because another thing that comes with this is angles are no longer limited in their measurement. When you guys measured angles, you used a protractor. Where's my protractor? You'd line it up with one side. Say, okay, so that's my starting value, which is the lower of the things, and then you essentially went around the protractor to figure out how many degrees it was. Do you notice that my second side doesn't actually fit on the protractor if I follow the path that it goes with? Because when you guys deal with angles just as pure measurement, the biggest angle you come across is 180 degrees. Because the moment that it got past 180 degrees, you just measured it the other direction. That doesn't work anymore. Angles have infinite measurement. Angles can have negative measurements. If the angle is going counterclockwise, it is a positive angle. If it's going clockwise, it is negative. Now, a lot of people are like, why? Why the heck is counterclockwise positive while clockwise is negative? And it has to do with the quadrants. On a graph, you have 4 quadrants. That one, that one, that one, and that one. Do you remember how they're numbered? No, this is typically a bit. This is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. They follow a C shape. And so the angles follow that order, going through quadrant 1 to 2 to 3 to 4. That is why counterclockwise is positive and clockwise is negative. One other key thing that is a big change today. Angles, yeah, we're going to measure them. And by measure, I don't mean like pull out a protractor. I mean we're going to work with information about their measurements. In the past, you've always measured them in degrees, but it's not only degrees. They can be measured in degrees, or they could be measured in what's known as radians. So, today we're introducing the idea of working with radians. What does a radian sound like? Sounds like a radius, and there's a reason for that, because a circle's radius is directly connected to radians. A measure in radians is the number of radii in other words, the plural of radius, traveled by an angle around a circle. Let's work with the idea of, let's say I have a circle there. Yes, we're going to pretend that I can draw a circle really well on the active board. I can't, but we're going to pretend that that is a beautiful circle. The number of radians for this angle would depend upon how far around we go to get from the angle's initial side to its terminal side. And we would measure that unit in an amount of radiuses, an amount of radii. For example, if the radius of this circle, distance from here to here, if this were 3 is hard to read up there in that color. If that distance were 3, then the number of radians that this would be is how many times 3 fits around this. So let's say 3 fits around there. Once, okay, this distance, okay, that appears to be about 2 3s. This appears to be like 3 3s. Now that's not a perfect measure of radians, but it would be like placing this distance around the edge and seeing how many of them actually fit. That's how radians work. Here's the thing. If I talk about that circle, how many radii actually fit around its edge? You have all the information to know the answer to that question. Every single one of you went through geometry. If I want to go around the edge of the circle, what is the edge of the circle called? It's the circumference. If I want to go around the circumference of a circle, I'm essentially asking how many radii fit on there. What do you know about circumference? Nothing about radius squared. You're thinking area. Has pi involved? Pi times radius times. It's not just pi r. It's no. That's area. Something pi r. Nope. Something pi r. Not half. Go the reciprocal. 2 pi r. Circumference is 2 pi r. And if circumference is 2 pi r, how many radii fit around the edge of the circle? 2 pi. 2 pi of them fit around the circle. It's about like 6 point something. Pi is 3.14159, etc. So, if you want to go all the way around a circle, which is 360 degrees, that is equivalent to 2 pi radians. Now, one of the things we're going to be doing today is converting from radians to degrees and vice versa. Now, y'all have converted units before. You would have done it back in like 9th grade chemistry, you would have had an entire section where you learned things like, if I have 5 miles per hour, and I want to change it into feet per minute. You put the 5 over 1, you had miles on top, hours on bottom, and then you multiplied by another fraction. In that fraction, you put miles on bottom, that way the miles would cancel out, and you can change miles into feet. And you would say for every 1 mile, there's 5,280 feet. Don't quote me on that number, that is me trying to go off of memory. I think it's actually 5,260 in hindsight. But don't quote me on that number either. And then you would multiply by another fraction. Miles would go away, now you have feet per minute. Or sorry, per hour, but I want to change minutes. So I put hour on top and then minutes on bottom, and for every 1 hour, there's 60 minutes. Hours would cancel out, and then you'd multiply your fractions straight across. This looking somewhat familiar to anyone? As something that you did? I promise you all did it. Every single one of you did it. You might not remember it, and that's okay. The key thing you need to know is, generally speaking, when you are trying to convert from one unit to another unit, the traditional way of doing it is to take what you started with and multiply it by a fraction that compares a unit you're wanting to change. So if I want to convert from degrees to radians or radians to degrees, I want a fraction that compares a number of radians to degrees. We have 360 degrees equals 2 pi radians. More traditionally, we want smaller numbers. In other words, I really don't want this 2 happening on the pi if I don't have to have it, because both these divide by 2. 180 degrees is pi radians. And that is going to be the key conversion number that we use. If you want to convert from radians to degrees, you are going to take the number of radians that you have, and you are going to multiply it by the fraction. If you have radians, you want to get rid of radians. If you have radians and you changed it into a fraction, radians is on top. To get it to cancel out, I need radians then on bottom of my second fraction. Here's my conversion. Radians will go on bottom, has pi, and degrees will go on top. If I want to convert from radians to degrees, I multiply by 180 over pi. If I want to go the other direction, if I want to convert from degrees to radians, technically I have that degrees in a fraction. The actual unit degree would end up on the top of the fraction, and I want it to cancel out, which means the fraction I multiply has degrees on the bottom. 180 degrees on bottom, pi on top. So, one of the things you're going to see today is talking about conversions. Converting to degrees or converting to radians, depending on which one it's starting with. 120 degrees? I have degrees, I want to go to radians. So I take my 120 degrees, I multiply by the fraction. Since I want degrees to go away, I put degrees on the bottom. I know that 180 degrees is pi radians, so the 180 goes on bottom, pi goes on top. I want to multiply fractions. You multiply straight across. Calculator is not going to be the most helpful thing for all of this. Some of it will, some of it won't. Straight across, 120 times pi is 120 pi. What's down here? Right here, though. Technically, in under 1, it's over 1. 1 times 180 is 180. Radians are written as simplified fractions. Pi is an irrational number. Therefore, if you put it into a fraction, if you put it into your calculator will give you a decimal. It will not have the ability to change it back to a fraction because it's irrational. Pi cannot be written as a fraction. In other words, pi is going to stay there. You simplify the 120 over 180. 120 and 180 both divide by what number? Both divide by 60. What's 120 divided by 60? 2. What's 180 divided by 60? It's 2 pi over 3. You can use your calculator to help you simplify, but you don't put the pi into the calculator. You put the pi on the answer. The calculator, you would just do 120 over 180 and make it simplify the fraction. It's the reason I jumped out of my skin. Dead spider. I didn't know it was dead at first. Pi over 11. Malia, am I currently in degrees or radians? Radians. How do you know? There's no degree symbol. That's exactly right. If there is no degree symbol, it is in radians. That means that if you are giving me an answer in degrees, you better have a degree symbol. Because I can write radians without a pi involved. There is such thing. We won't see it very often, but just make sure that if you are working with degrees, you write a degree symbol. Okay, so we're working radians though. Ella, if I want to go from radians to degrees, what am I going to multiply by? Is it 180 over pi or pi over 180? 180 over pi. Do you notice that there is a pi on both top and bottom of the fraction? They die a painful death. I don't know if the spider died a painful death, but it died. Okay, 11 on bottom, 12 times 180. 2160. Do we leave degrees as fractions? No, we divide them. $196.4. Don't forget to put the degree. A couple more examples of this, and then we're going to shift. Well, yes, there will be lunch involved. There's also one other thing we're doing today. No. It's not notes all day. Okay, negative 75 degrees. Lisette, if I want to convert this to radians, because I see the degrees, what am I multiplying by? Times pi over 180. Degrees, die a painful death. One of the most common things that I see popping up is that people lose that negative along the way. Negative times a positive, negative. Pull the negative out front. I get 75 pi over 180. Can I simplify the fraction? Yes, if you can simplify it, do so. What does it become? Negative 5 pi over 12. Would you agree that converting is fairly simple? Yeah, converting is not meant to be challenging. It is a key thing that we are going to do on a lot of things, though. There is a second thing you're going to see today. Is sketching the angle in standard position. Enjoy your lunch. So, if you want to sketch an angle in standard position, remember what the requirements for standard position were. Vertex is on the 0, 0 on the origin. Initial side, positive x-axis on the right side. And then we got the terminal side going through. Counterclockwise is positive, clockwise is negative. So we need a coordinate grid. We don't need a big one. When you are sketching an angle, it doesn't have to be perfect. You just have to be able to kind of get the general idea. It does not have to be a big graph. I make mine tiny. I start by putting the vertex on the origin and the initial side on the positive x-axis. From there, next thing I check is positive or negative. Positive, telling me I'm going counterclockwise. So I need to go counterclockwise 215 degrees. How many degrees is a full circle? 360. How many degrees is half a circle? 180. A quarter of a circle? 90. So, I need to go counterclockwise. Okay, if I were to stop here, I would have gotten 90. If I would stop here, I'd get 180. I don't need to go another full 90, right? Just a little bit further? Kind of like here-ish. Finish off my arrow to indicate that I went this direction. There we go. There's my 215 degree angle. Negative 320 degrees. Vertex here, initial side here. Clockwise or counterclockwise? Clockwise, because it's negative. Start here, I go here. How far have I gone? 90. How far have I gone? How far have I gone? Do I go another full quarter? No. I'm already at 270. I just need an additional like 50 degrees. So about half-ish way through. There we go. Not too scary? Now there's some things that mess with people with this. Such as when I do things like this. And I give an angle bigger than a full circle. You do the same thing, you just have to spin around to get there. Clockwise or counterclockwise? Counterclockwise because it's positive. It's more than 360, which means I am guaranteed to at least have to go a full circle. If I go an additional 90, how far have I gone? 450. 360 plus 90, 450. Okay, that's not quite far enough, so I know I'm going at least this far. Still 30 degrees shy. So a little bit further, but not that much. Finish off my arrow to make sure it's clear what direction I went, and there we go. One more in degrees, and then let's talk radians. Negative 770. What do I know? Clockwise. Compared to a circle? Bigger? Full circle would be 360. If I go 360, how much further do I have left? I've got an additional 410 degrees I have to go. Also bigger than a circle. Which means I'm making another loop around. 2 full circles, how far have I gone? 720 in the negative direction, but 720. So I need an additional 50 degrees. Not a full quarter of a circle. So I'm ending up somewhere down here. Finish my arrow so I can tell which direction I went. How we feeling about sketching angles and degrees? Really all comes down to knowing full circles are 360, quarter of circles are 90. The same idea works when you're working in radians, but it trips people up a little bit more. 1, because it's fractions. 2, because of the pi that's in there. And 3, just because you're less familiar with radians overall. The same general principles apply. Clockwise or counterclockwise? It's positive. We're going counterclockwise. What is a full circle in radians? 2 pi. What's a half circle in radians? Pi. What's a quarter circle in radians? If a full circle is a pi, if a let me try this again. If a half a circle is a pi, a quarter of a circle is half of that, half of a pi, or a pi over 2 is traditionally what it's called. Here's the main thing you got to know when it's in radians. Radians, when I ask you to sketch it, are always going to have the pi on them. A full circle is 2 of them, a half circle is 1 of them, a quarter of a circle is a half of a pi. So, ignore the pi altogether, look at the number, 3/4. If it helps you to think about it as a decimal, think about it as a decimal. 0.75. Would you agree with me that 0.75 is less than 1? Would you agree with me that it is bigger than 1/2? If it is less than 1, aka less than 1 pi, it is less than half a circle. If it is bigger than 0.5, in other words, bigger than a half a pi, it's bigger than a quarter. From here to here is a 0.5 pi. If I went all the way to here, it would be a full pi. I don't want a full pi. I want 0.75 of the pi's. So I go bigger than a half, but smaller than a whole. Sorry. Bigger than a half a pi, smaller than a whole pi. Half the circle is 1 pi. That's what messes with people. People like to think of a full circle as a full pi. Half a circle is a full pi. Eight pi over 7. Clockwise or counterclockwise? Counterclockwise, it's positive. Ignore the pi. 8/7. Bigger than small 1. Generally, a quarter of a circle counts a 0.5. Bigger than 1 but smaller than 1.5? Point 0.5, 1, a little bit further than 1. I got 2 more examples, then we're done. Negative 12 pi over 7. Negative tells me clockwise. 12 over 7. 1.7-ish. Starting here, going clockwise. Every quarter of a circle is how much in radians again? 0.5 pi, so here's 0.5. There's 1. I want 1.7. Here's 1.5. Need to go a little bit further. Final one. Negative 13 pi over 6. Clockwise or counterclockwise? Clockwise, it's negative. 13 over 6. 2.16. Quarter of a circle is 0.5. Half a circle, 1. 3/4 of a circle, 1.5. Every one of these is 0.5. So 0.5, 1, 1.5, 2. Don't want to get to 2.5, but I do need to go a little further. There's my angle. If radians really messes with you, and for some people it does, and it happens. Worst case scenario, can you convert from radians to degrees? Yes. And once it's in degrees, then you can see it a little bit better. Today's assignment's really broken up just because we haven't gotten to a couple of concepts in the section. It's also the homework assignment that people tend to finish the fastest.